Good afternoon, and thank you for joining us today. My name is Erin Williams, and on behalf of the Association of Schools and Programs of Public Health and the National Board of Public Health Examiners, I welcome you all to today's presentation. It is the CPH Review Session webinar presented on environmental public health, the biological basis of human disease risk. Today's review session is presented by Dr. Michael Bessesi, Senior Associate Dean and Director of Academic Affairs, Professor and Chair of Environmental Health Sciences at Ohio State University College of Public Health. This and all of our CPH Review Session webinars are archived on the NPHE website for future viewing. The PowerPoint presentation as well as the recorded webinar will be available for you at a later date. There are also archived copies of all past presentations, and any future presentations will also be posted here. To submit your questions during or after the presentation, all you'll need to do is type your question into the chat question box, which is opened by clicking the small white arrows that are on the upper right corner of your screen. Now it is my pleasure to introduce Dr. Michael Bessesi, who will be presenting today's review session. Mike?
Great. Thank you, Erin, and welcome everybody. So we're going to spend approximately the next 2 hours together providing you an overview of material relative to the CPH exam, but certainly no guarantees that every question on the exam will be covered by this presentation. Having said that, you can see the purpose of the webinar and the module that we will be conducting this afternoon. And I looked through some review guides from APHA and also review website material from ASPPH, and I got a feel for the types of questions that are asked in the review guide and review materials. And so this module includes that kind of information. And so I'll say this quite simply. This presentation will present more than enough information, I suspect, to help prepare you for CPH exam for the individual domain that I'll talk about in a moment, but certainly not enough information if you were sitting for the Registered Environmental Health Specialist exam. So it's somewhere in the middle, and I will gauge how much depth to cover as we progress. So this slide is a modified slide. I took some liberty, but this slide is from the National Board of Public Health Examiners. And my understanding is this webinar is the first one relative to environmental health content for the new exam, the revised exam, based on the modified public health domains that you see in the first column. And the yellow shading shows where environmental and occupational health content or environmental public health content really crosses most of the domain areas. However, having said that, most of the emphasis today will be on public health biology and human disease risk, or as I've modified it, environmental public health. And this listing of these 4 domain tasks is from the National Board of Public Health Examiners. I'm not going to read this to you, but just if you haven't been to the website, you'll see that these are applicable to the specific domain that I'm presenting. And then more specific to the presentation in this module are some learning objectives that you see in the bulleted list on this slide. And we will begin with some fundamental principles to set the stage, if you will, and then we will progress in more with more specificity and application as we progress through to this module. And this is a bulleted list of the topics. And I plan to get through most of these topics. I've added more than enough slides to assist you in a in what I'll say is a relatively comprehensive but nonetheless succinct overview of content to help you prepare for the CPH exam. And again, I'll cover most, if not all of this. If we don't cover it all and you have questions and so forth that can't be addressed during today's session, Erin and I will work with you to email you some additional content or links to content to assist you. So we'll begin with the first section and ask the very fundamental question of what is the distinction between hazards and risks. And so this is important because we are going to talk about categories of hazardous agents and subcategories within those. And so it's important to understand the distinction between these words. They're sometimes used as if though they're synonyms, but they are not. And so hazard has to do with the inherent characteristics of a given agent that make it harmful in some way, whether it's toxicity or infectivity or corrosivity or all the above, depending on the circumstances. And equally, if not more important from the perspective of exposure science, is answering the question of potential for exposure to occur. So sometimes we speak in terms of what is the hazard potential, because you can have a hazardous substance, but unless you're exposed to it, there's negligible to no risk of initiating any disease. So there's only risk of initiating disease when there's exposure. And I'll be spending a considerable amount of time throughout this presentation referring back to the concept of exposure and hazard potential. So you see, risk then has to do with the probability that an adverse response will be manifested following exposure. But not all exposure initiates disease. Again, this will become more apparent as we progress through. And so this is a little more detail, but the focus of this course, although towards the end there's a brief topic on One Health, the focus here is on the receiver of exposure being humans, so not so much animals and so forth, but the specific focus is on population health with specificity to humans and how the human exposure occurs at the interface with the environment in various settings, indoor, outdoor, and so forth. And then risk, that probability, I've included the diagram about the 4-step risk assessment process. I think it's important for you to be able to differentiate between risk that is qualitative and risk that's quantitative. You don't need to certainly know how to conduct a risk assessment, but you see that within the 4 steps here, hazard identification is a fundamental starting point, and then answering the question, what are the dose response? And this model originally was almost exclusively focused on chemical agents and some degree radiological agents, but quantitative microbial risk assessment for infectious agents, infectious diseases follows a similar paradigm, where we want to know what this substance is, what are the inherent characteristics of it relative to causing toxicity or infection or allergy even for that matter. And then there's a component here highlighted in yellow that you actually have to assess the level of exposure. So you will see as we progress through this that there are actually multiple components that come into play and then are incorporated in the actual risk characterization formulas to conduct a full risk assessment. But said differently and much more succinctly, to assess risk, you need to know the hazards involved, the characteristics of those hazards, the exposure levels, and the population of concern. So then, what are these hazardous environmental contaminants, and what do they have to do with that interface between human and their environmental settings relative to exposures, and following exposures, the probability that there will be a change such as an increased risk of initiating some type of related disease. And so this focus today will be on three categories: biological agents, chemical agents, and physical agents. And it's important that you have this inventory in mind, because it does assist, and then I'm talking right now, whether you're participating solely for the exam or simply strengthening your knowledge and understanding beyond the exam. It's important to at least have a grasp of the distinction between these. So when we talk about pathogenic agents, that word is actually broader than it's used, but we're typically referring to those microorganisms that are related to infection, and they fall under the category of biological agents. And when we talk about vectors that can be involved in the transmission of infectious agents, those are living organisms as well. And representatives could be insects such as flies and mosquitoes, and arachnids such as ticks, and a little more content on that later. When we talk about the category of chemical agents, most of the focus from an environmental public health perspective is on toxic chemicals. But as you'll see in a few moments, there are other subcategories, but less important really to understanding environmental public health, more important in the broader categories of understanding hazmat or hazardous materials, or occupational health or industrial hygiene. And again, I'll come back to that. And then finally, the third category, the physical agents. I'm going to highlight just some aspects of differentiating between the two major categories of radiation, or subcategories of ionizing and non-ionizing radiation, the distinction between the two, and just highlight a couple of key sources that you should be familiar with relative to environmental public health. And then I'll talk a little bit about noise as well. I will not be spending time on temperature fluctuations and extremes, but climate change does come into play here with temperature fluctuations and extremes. I'm just not spending much time on that today. So when we talk about the category of biological agents, the subcategories include the organisms, viruses, which are technically non-living organisms. They're really biochemicals, and then the actual living organisms, bacteria, fungi, protozoans, and helminths, which are parasitic microscopic worms. And so these agents are associated with infection, and so they can initiate an infection, but there's some exposure steps that are involved that I'll come back to a little later. And this slide shows the subcategories of biological agents in a little more detail. Most of the focus on environmental public health has to do at the microbial level, not so much at the mesoorganisms such as plant pollens, or even macroorganisms such as venomous snakes and so forth. But the point here is that when we talk about infectious agents, infectious diseases, it's exclusively focused on the microorganisms, viruses, bacteria, fungi, helminths, right? And then when we talk about allergenic biological agents, it can include some of these microorganisms. Molds is a major example there, but also plant pollens, much higher level in terms of size and so forth. And finally, some types of biological agents across the spectrum, going from microorganisms to macroorganisms, synthesize biochemicals that are toxic. And the word toxin specifically refers to toxicants that are synthesized by biological organisms. So Clostridium botulinum is a major example you should be familiar with. And so the botulinum toxin is synthesized by the bacteria, and this is one example, but there are other toxins or biotoxins synthesized by higher scale organisms as well. But again, I want to emphasize from the perspective of environmental public health, focus should be almost exclusively on the microorganisms. And the next few slides go into a little more detail. And so most of my emphasis will be on the infectious microorganisms. So I want to spend just a few more seconds on this particular slide and not as much on the subsequent two slides. But when we say infectious microorganisms, this refers to organisms that can proliferate within a human system. But before we even concern ourselves with proliferation within a system, we have that understanding of hazard, so the inherent hazardous characteristics of the organisms or agents involved, but also the hazard potential, and that is the likelihood that exposure occurs. So this assumes that exposure occurred, and only after exposure occurs can the organism proliferate within the system. And another point here, which is just a point of trivia, if you will, is that just because exposure to an infectious agent occurs, it doesn't automatically mean that the person exposed has been infected. They've been exposed. But for a variety of reasons of modes of elimination, whether it's coughing it out, sneezing it out, involving comprehensive immune system response, true infection occurs when there's this proliferation occurs and colonization of those organisms. For example, a respiratory infection or a gastrointestinal infection doesn't mean simply that the organism is present in that system, but it implies that there's been proliferation resulting in colonization of those organisms. And then that, along with the virulence of the organism and the host's immune response and resistance to infectious is related to the potential to initiate disease or risk of initiating disease. And again, we'll be coming back to this throughout. And then again, less likely to be emphasized, in my opinion, within the environmental public health, but I think it's important to understand that many of these biological agents are related to the allergic response, which again involves the immune system. So it's not a true infection necessarily based on proliferation and colonization, but the antigen antibody response. And if you were to know one subcategory of microbes, it would be mold. Not the only one, but certainly probably the most popular one. And then third, the toxic microbes, as I already mentioned, refers to those that specifically synthesize a biochemical toxicant that's specifically referred to as a toxin or biotoxin, and that in turn can have a dose response effect very similar to toxicants that are of chemical nature, such as solvents or metals and so forth. So it's not the organism directly necessarily, but the toxin, and the toxin is active with or without the organism. Moving to the second category, the chemical agents. When we talk about the chemical agents, there are really two categories: the inorganic, such as the metals, and the one that's probably most popular within environmental public health, or the highest awareness among the public health in general, is lead, which is a major example of a metal. Certainly not the only toxic metal of concern, but a major one, because it's found in air, it's found in water, it's found in soil, just to name three major matrices. But we also have some concerns of some other inorganic chemicals such as nitrites and nitrates, more of a concern in drinking water, well water, associated with methemoglobinemia, for example, oxides of nitrogen, oxides of sulfur relative to ambient air pollution and so forth. And again, a little more on that as we progress. As far as organic chemicals, most of the emphasis is on organic solvents that are used for industrial purposes, pesticides, including insecticides and herbicides and fungicides that are certainly present in the environment. And they come in various forms. And but when we look a little deeper at subcategories of chemical agents, you see that it goes beyond toxic chemicals. It also includes flammable and combustible chemicals, corrosive substances, which actually could fall under toxic substances, and those substances that are reactive or even explosive. So there are really four major subcategories under chemical agents, but the one of most relevance to environmental public health, as I stated earlier, are the subcategory of the toxic chemicals. And they're toxic because they have the potential to produce abnormal biochemical and related physiological response when an individual is exposed. And those are the substances we refer to as poisons. So the reality is all chemicals have some level of toxicity, but not all toxic chemicals are flammable. Not all toxic chemicals are corrosive. Not all toxic chemicals are explosive. So, but overall, all chemicals have the characteristic of being toxic at some level, some more potent than others. And the third category, the physical agents. When we talk about physical agents, you know, if we take a step back with biological agents, we're talking about organisms, for example. When we're talking about chemical agents, we're talking about elements and molecules and compounds. When we're talking about physical agents, we're really talking about energy. And that energy, from a human exposure perspective, more generally from an environmental public health perspective, is energy that's transmitted through air. And so we look at these energies in the form of electromagnetic waves, particles such as alpha, beta particles, and electromagnetic waves such as gamma rays, ultraviolet rays, microwaves, and then X-rays, and then pressure. And pressure refers to the physical agent subcategory of sound or unwanted sound that we call noise. And so these are some of the specifics, generalized specifics that characterize physical agents, and these represent three major subcategories. Now, looking with a little more detail, and we'll come back to this later, is the toxic radiological agents. And the two subcategories are ionizing radiation, and a major one of public health concern, not the only one, but the major one. You should be familiar that radon gas associated with soil, which is generated from decomposition, originating with decomposition due to unstable uranium, forming a series of radioisotopes and a precursor of radium, which undergoes further radioactive decay to release radon gas, which can diffuse from soil into sub-basement levels and create elevated levels of radon gas. More on that in a moment. The second subcategory is the non-ionizing radiation. And the distinction here is non-ionizing radiation is electromagnetic radiation. So it's 100% wave-like. Ionizing radiation can be particle-based, as I already alluded to. And again, more on that. But what they have in common is energies, and these energies can interact when there's exposure and interact molecularly and subcellularly to initiate vibrational and thermal changes that result in alterations of biochemistry. That's the structure and physiology, the function at the subcellular level with manifestation at the system level. And so the distinguishing characteristic between ionizing radiation and non-ionizing radiation has to do with the level of energy. And so ionizing radiation is associated with higher energies that are released, that they can actually break bonds and result in ionization. So for example, radon gas, when inhaled, radon gas is a major example of ionizing radiation, and the interaction is it actually ionizes water molecules, which most of our composition is water, and it converts those water molecules into free radicals that then initiate a chain reaction of events that can damage biomacromolecules and ultimately cells and tissues and a whole organism. Non-ionizing radiation can be very damaging as well, but the energies are lower. Again, typically lower than 10 electron volts if you want a quantitative threshold, and by virtue of being lower, the impact is more vibrational and thermal rather than an ionization event. And so we think of the interaction of ultraviolet rays, sunlight, ultraviolet rays, UVB, for example, microwaves from microwave ovens, but also microwave communications. ELF stands for extremely low frequency non-ionizing radiation. So again, more on that later. And shifting to sound, when we talk about sound from an environmental public health perspective, there's really two settings where sound comes into play: the community-based sound and the occupational-based sound. And occupational settings, sound, or more specifically unwanted sound, which is noise, depending on exposure conditions, is associated primarily with noise-induced hearing loss. But outside of the occupational environment, more the community exposure from airports and other transportation sources such as trains and nightclubs and so forth is associated with more physiological distress, psychophysiological distress. So it's a stressor creating some anxiety, disruption to sleep, etc. But community-based noise is not associated with noise-induced hearing loss. Noise-induced hearing loss, to intentionally repeat myself, is associated with a workplace or occupational settings, not so much with community-based settings. So looking at radon gas, here's a good, two good diagrams for you to consider. And so the middle diagram just shows you the concept of radioactive decay. And when we talk about ionizing radiation, the radiation can be in the form of particles. As I stated, it could be an alpha particle, which is very heavy and dense. So radon gas is associated with liberation of the very heavy alpha particles. So it's more of an internal radiation hazard. You have to inhale the radon gas into your respiratory system to initiate any damage that may occur. And again, it has to do with the levels of radon gas and the duration of exposure. So it's, but the other particles that are associated with other types of ionizing radiation, unstable radioisotopes that generate ionizing radiation will generate beta particles, for example, and positrons and negatron beta particles. And then there's two examples of electromagnetic radiation from ionizing, and that's X-rays and gamma rays from ionizing radiation. But the diagram on the far right shows you that the decay of unstable radioisotopes that's associated with generation of radon gas that gas can diffuse through various openings in the subsurface areas, basements, right? And that gas can accumulate. It can also diffuse through the dwelling or the structure. It's not limited to homes. It could be any dwelling that has a basement level. And also, if there's reliance on well water, radon gas can be in well water. And another way of getting that inside a building is turning the water on. So radon gas can diffuse out of shower heads and faucets and so forth, if indeed well water is involved. And again, it's ubiquitous. The key is answering the question, how much radon gas is actually present. And the EPA has a level at the federal level. It must be below 4 picocuries per liter of air for clearance inside a facility. Shifting to non-ionizing radiation. So I'll repeat, ionizing radiation is certainly associated with ionizing radiation with particles and electromagnetic forms. So again, particles, alpha and beta particles, just to name two. There's also positrons and negatrons, but under beta, but there's neutrons and protons too. But again, that's beyond the scope of what you really need to understand it for this purpose. But there's also electromagnetic forms. So gamma rays and X-rays are electromagnetic waves, but they're categorized as ionizing radiation because the energy associated with them can initiate ionization reactions. The other forms of electromagnetic waves that you see in this diagram here, so the blue arrow, it begins with ultraviolet all the way over to the left, the extremely low frequency forms of non-ionizing radiation. So everything under this blue is electromagnetic, meaning it's waves of energy, where under the yellow you have a combination of either X-ray or gamma ray in the electromagnetic spectrum. So that's the point of showing this. So what is the application? What is some major examples of concerns from an environmental public health perspective? Well, UV light, specifically UVB rays from sunlight, natural sources, microwaves from communication towers, but microwave ovens that can leak. And then this spectrum here, the extremely low frequency coming from electronics, including those in the home. It's improved over the years. Computers are designed now to emit much lower levels of extremely low frequency non-ionizing radiation. But power lines are associated with the electromagnetic rays in this range. So these are just some examples. And then moving to sound, I want to emphasize, if this is somewhat new or this is a refresher, that it's really noise that we're concerned about. What is noise? It's unwanted sound, and it's normally unwanted because it creates disturbance, and that's what community-based noise is. It's disruptive, and that disruption can initiate psychological stress with associated physiological responses. So we say that community noise is associated with psychophysiological responses, not the noise-induced hearing loss, as I mentioned, but unwanted sound in the workplace can be related to that. But in addition, because of elevated sound levels based on amplitude and frequency, is associated with noise-induced hearing loss. So this represents the wavelengths. It's sinusoidal of energy, is the vibration of air molecules is sinusoidal in nature. And the higher the wavelength, the louder the sound. This is the amplitude. And this line here in these graphs represents atmospheric pressure. And so as you project the sound, the louder the sound, the higher the amplitude, because it creates more pressure deviation from the baseline of atmospheric pressure. And so loudness has to do with the amplitude, and pitch or frequency has to do with wavelength. So number 4 is higher frequency, and then number 3 is lower frequency because it has a longer wavelength. So shorter wavelengths means more wave cycles within a given time. So the measured in hertz, loudness is measured in decibels, and you can see comparing 1 to 2, the amplitude is higher, so 2 is louder than 1. And then when you compare 3 to 4, 4 represents same loudness but higher frequency because of the number of wave cycles. So let's shift and talk about the matrices, because for exposure to occur, there's typically sources of contamination. And the sources is from 2 directions. There's sources that contribute to contaminating a matrix, and then once this matrix is contaminated, that becomes the source of exposure. So this diagram shows you 4 major categories of environmental matrices: air, water, soil, and food. And a little later, I'll give you some specific examples relative to air, water, and food. And I won't be covering soil. But the point is there are sources here. You can see in this photo of manufacturing industries, the emissions from that. So this is the primary source, but then the emissions contaminate the air, and now the matrix air is contaminated. And if you inhale that air, then you are exposed. And the same concept holds to water and soil and food. And so when we talk about the environment, you have to recognize that there are various environmental settings. And so there's workplace settings, so industries and manufacturing facilities, offices, schools, hospitals, agricultural settings, just as most of the examples, and non-occupational, such as our homes, our dwellings, apartments, and so forth. But it also includes outdoor environment as well. So the ambient environment is certainly part of the discussion when we talk about it. So now I'll apply this and we'll talk about the major pathways and modes and routes of human exposures to environmental contaminants. So looking at this with a little more detail, from the perspective of 5 categories of matrices, beginning with air, water, soil, and food, you can see that we have some categories beneath each in which we categorize this. So when we talk about air being contaminated or polluted, that means that it's the air anywhere. And the only really distinction is, are we talking about outdoor or ambient air, or are we talking specifically about indoor air? Again, that air inside a factory of occupational exposure concern, the air inside our apartments or homes, so indoor air quality concerns. And then shifting to water, we have various categories of water. It's not just looking at water from a drinking perspective, but the source of that water and the uses of that water. So the first 2 refer to sources of water: surface water being exposed to the air, groundwater being underground in aquifers. But then how is that water used? Is it used for drinking and cooking purposes, bathing, irrigation, fishing, swimming, etc.? Soil can be categorized as well, but for the purposes of environmental public health, it's less important, so I'll just leave it generically as soil. And then food, including beverages, is really primarily categories of plant-based and animal-based food. I've added a 5th category, if you will, of a matrix that can contribute to pathways of exposure. And the first being vectors, which are living organisms that can be a means of transporting, first of all, they're living organisms, but they can be a means of transporting an infectious agent, for example, such as West Nile virus, from a contaminated host to a receiving person who then gets bit, and then the virus is transmitted to a receiver of that. So I'll show you some diagrams of this later, but vectors and vehicles are certainly other categories that we can include when we talk about matrices and then related pathways of exposure. And so I've included the next two slides, some photos that, we may take for granted, but when we talk about contributions to air contaminants, specifically chemical air contaminants in particular, we have stationary sources such as factories, we have mobile sources such as vehicles, and we talk about receiving bodies of water. You can see that this discharge is coming from some source and discharging wastewater, or in this case, it's actually storm water, into a receiving body of water. This is a surface body of water, but the ramifications of this downstream could be contamination that's either visible or not. Crowding and so forth contributes to air contamination from the perspective of sound, and then we have soil contamination, food contamination, and so forth. So they're really all interrelated, in some cases more so than other, but we talk in terms of exposure, and we use the word the interface between humans and their environment. And if we were talking about One Health, we would include non-human animals in that discussion as well. And then shifting to another category, various types of workplace and residential environmental settings. It varies, and it can be indoor settings, outdoor settings such as agriculture, and you can see that from the occupational setting, there's a potential for higher levels of exposure by virtue of the specific processes involved. So looking at this, the consumer could be exposed to the herbicides being sprayed on this vegetation if it's not washed properly. But even so, some of this material can infuse into plant material. There's more work on that being done. But if you were to ask the question from an environmental public health perspective, who has the higher hazard potential based on potential for exposure, consumer of this vegetation or the worker who's applying this herbicide? Well, clearly the worker, assuming inadequate personal protective equipment, has a higher likelihood of exposure and therefore a higher hazard potential than consumer. Both may have risk, but the likelihood of higher levels of exposure, the risk of initiating herbicide-related disease is probably higher in the worker than consumer. And that holds true mostly in general when you compare occupational settings to non-occupational settings. And so this is one model, a very simple model of the concept of exposure contributing to the risk of disease, and it has to begin with exposure. And then once somebody's exposed, the question is what factors contribute to increased susceptibility to disease, and then how much has been absorbed or accumulated at the target site. So if it's the lungs or the kidneys, we talk in terms of a biologically effective dose or the toxic dose that accumulates. And then depending on a variety of factors, what is the biological response, or what are the adverse effects or disease associated with that initial exposure. But it doesn't jump simply from exposure, meaning there's automatically disease. There's several factors that come into play. And so looking at this from the perspective of dissecting exposure into three categories, this is simply another way in which I present the concept of exposure. So there's environmental agents, there has to be some form of contact with the human, and that would be called external exposure. And then there needs to be some level of absorption, either at the local level or more systemic level, resulting in internal exposure. That's a dose. And depending on a variety of factors, host susceptibility, for example, if an adverse effect occurs, we call that effective exposure. And that is manifested by alteration of structure, specifically beginning at the biochemical level, and then function, meaning physiological changes, and then a manifestation of what we would designate as disease or dysfunction. So we always need to ask at least two fundamental questions when we talk about exposure, and that is, what is the level of exposure and what is the duration of exposure? And again, not only those two, but it really begins with that. And there can be local exposure at the point of contact. More on that in a few seconds. And then if there's absorption systemically, there can be systemic effects as well. And so environmental sampling is used to measure levels of external exposure when feasible. We can measure air contaminants, whether chemical or radiological. We can measure biological, physical, and chemical agents just in general. And we can either estimate or measure duration of exposure. So said differently, we can characterize external exposure. And then it crosses over in which you can use models to estimate the amount of absorption and internal exposure and the risk of initiating disease, and or you can also involve medical monitoring as well. So sampling of blood and urine is examples of two tissues among others. And then as you'll see, epidemiology, in my opinion, crosses and really is at that interface between environmental public health relative to external exposure and medical monitoring and surveillance relative to internal exposure and infective exposure, right? So ultimately, the impact or response is what we're trying to avoid. So prevention, primary prevention really means controlling the contaminants at the source so we don't progress to this state, because this is what we're trying to control, the scope and levels of contaminants in the environment. If you control it here, that's a primary prevention. And therefore, by reducing the scope and levels of contaminants in the environment, you decrease the hazard potential and you would decrease the risk for morbidity and mortality. But this demonstrates very simply if it progresses unchecked. So we asked the question, how are substances, how are we exposed to substances and where? And you see in this table, there's really four major modes of entry, how we're exposed. You can inhale contaminants from the air, and the initial portal or route involves the respiratory system. You can ingest contaminants from food and water intentionally, or you can ingest materials while swimming, water while swimming unintentionally, and that would involve the initial contact with the gastrointestinal system. And thus you can understand why inhalation often involves local effects involving the respiratory system, infection, irritation, to name two examples, where ingestion of an infectious agent, a pathogen, often targets the gastrointestinal system. Not only, but that's certainly a major target site. The third category has to do with direct contact dermally or ocularly, and that's the integument system. And just if you're curious, the respiratory system is about 100 square meters of exposed tissue. Gastrointestinal system, more than 300 square meters of exposed tissue, whereas the integument is only about 2 square meters of exposed tissue, although all of these are important. And I've added a fourth mode, hearing, because vulnerability to noise-induced hearing loss, but even vulnerability to the psychophysiological impacts of sound begin with the auditory system. So hearing is the mode of exposure to sound, and unwanted sound is noise, and then the initial route or system involved is the auditory system, not exclusively, but primarily. I'm not going to spend time on the next few slides. They're here for your review. But again, inhalation mode, respiratory route, ingestion mode, gastrointestinal route, and then contact and dermal route absorption. And the point here is, from an environmental public health perspective, you have three major organ systems where initial exposure occurs, with the exception. There's a fourth category, and that would involve sexual transmission. And so I'm focusing here on what I would call more of the external exposure to biological, chemical, and physical agents. Three major systems, one or more would be involved, and the auditory system would be a fourth one if we're specifically looking at sound or noise. But the category that's not represented in this module is sexually transmitted exposure, but that's more often than not covered under epidemiology. And here's a diagram, physical, chemical, biological agents, just showing you the transition where it all begins. There has to be exposure. And so when we talk about hazard, what are the inherent characteristics of the categories and subcategories of these three categories? What are the inherent characteristics associated with causing harm? And what is the potential for exposure to occur? What are the levels of exposure? So everything begins with external exposure. If there's no external exposure, then there's no worries, no concern about internal exposure, and therefore there would be no worries or concerns about effective exposure. So again, prevention begins here. So we'll continue with what are some general categories and characteristics of adverse health effects. So again, there's that initial entry. So there's the absorption at a local level involving interaction at the cellular interface, but then across various membranes, the skin, digestive tract, mucosal areas where that absorption occurs. And then once something becomes systemic, meaning it's entered the bloodstream or the lymphatic system, it can be distributed to other organ sites. I'm not getting into the area of toxicokinetics qualitatively or quantitatively by any means, but really the absorption and distribution are the first two components of really a four-part where we would also include biotransformation or metabolism of these substances, and a fourth would be elimination, but that's beyond the scope of what I intend to do in this module. But you should know the distinction between acute and chronic, whether it's relative to exposure, short-term, single exposures versus chronic exposure, whether you're drinking contaminated water day after day, week after week, month after month, or inhaling contaminated air day after day, week after week, etc., versus just a single or a few exposures. So acute versus chronic exposure. And then there's effects. Not all effects are permanent, they're long lasting. So there are adverse effects with symptoms developing rapidly, such as irritation of the respiratory system, or even a cold, for example, could be considered an acute effect. But then there's a recovery in a relatively short period, minutes, hours, maybe days, in the case of a respiratory infection, for example. And that's in contrast to chronic effects, which develop over time. So chronic bronchitis, for example. So there's different factors that come into play, but from an exposure side, it's duration and rate of exposure, acute and chronic exposure, are critically important in the determining the hazard potential and therefore the associated risk. And then briefly, local effects are manifested at the site of initial contact. So going back to what I stated a few moments ago, looking at the respiratory system and the inhalation mode, looking at the gastrointestinal system or route and the ingestion mode, and looking at the integument, the skin and eyes, and that direct contact mode. If the adverse effect manifests at one or more of those sites, then that's determined to be a local effect. If absorption occurs and absorption results in systemic contamination, now the substance is in the bloodstream and it's distributed elsewhere, other organ systems may be involved. So an example with a chemical is inhalation of airborne toluene or benzene vapors, which are solvents, can result in irritation locally in the respiratory system. The presence of the vapors can result in irritation of the eyes, for example. And if those vapors cross from the respiratory system via the alveoli into the systemic circulation, they can be transported to the brain and cause acute narcotic effects. And long-term chronic exposures can involve other organ systems ultimately, the liver, for example, the bone marrow, depending on the substance. So local versus systemic effects. And then there's the concept of major target sites. And there's myriad target sites that can be involved. But if you look at this list here, the respiratory system, the dermal system represent where local effects can occur. The rest of these are systemic, and integument should be in here as well. Reproductive system could be added as well. So any of the organ systems are vulnerable. Remember, skin is the integument is an organ as well, but virtually any organ system it can have some related risk of change depending on the hazard characteristics, the hazardous characteristics of the agent or agents involved. Mutagens and carcinogens imply a little different in terms of mechanisms, and I restrained myself from, I deleted several slides that I incorporated in the initial drafts of this slide set, but if there's any interest, I can send more information to you in addition to this module that'll be available on the National Board website. But mutagens are a little different in mechanistically in that they result in actual changes to genetic information, either directly or indirectly. And the most common one of concern are the carcinogens, the cancer-causing substances, and primarily chemicals and radiological agents. But recent years, there's more indication that even biological agents, specifically some viruses, can be linked to cancers. So HBV, Epstein-Barr virus, and so forth as well. But when you talk about carcinogenesis, there first has to be induced changes, and that's associated with abnormal proliferation of cells, and then invasiveness of that, spreading of it, the metastasis, and then differentiation of cells, and leading to what would be diagnosed as a cancerous or carcinogenic effect. And here's a diagram where there's actually a direct genotoxic interaction, where there's some type of a bond formed between a parent compound or a metabolite from a parent compound with the DNA, altering the DNA and resulting in a mutation. And if that mutation is promoted and progresses, that can take on the characteristics shown here in this slide, which would determine whether it's categorized as being cancer-causing or carcinogenic agent. Okay, so to give you an example, polyaromatic hydrocarbons are very predominant in areas where there's high traffic levels and industrial levels. They are discharged from combustion sources. Benzoate is just one of several examples, but benzoate is classified as a procarcinogen. It's not cancer-causing in its parent form, which is shown here in the slide, but it can undergo, once exposure occurs in a human system, they're part of biotransformation. There are enzyme systems that designed to hopefully detoxify and eliminate hazardous chemical agents, but some actually result in changes that are make it more toxic, and this is a change to that original parent compound, so it's an epoxy ring. So it's no longer simply benzoate pyrene, it has the 7,8 epoxy ring, and that's the proximate, and ultimately that can change even further into the ultimate carcinogen, and this is the active form that can initiate that genotoxic event. And then again, a promotion and progression of those changes can result in the invasiveness and the metastasis and so forth associated with carcinogenic events. So just as illustration, again, if there's interest or you feel there's a need, I don't think specifically focusing on the CPH exam, there'd be a lot of this, but nonetheless, this is a classic example that you may find interesting. But if you want more of this, I can share more another time. And then finally, teratogens, which involve mutations, but they can be large mutations involving damage to actually chromosomes themselves, and again, typically related with chemicals and radiologic agents, and these can be genetic or somatic. Genetic implying that the developing embryo or fetus will manifest a mutation, but again, enough said at this point. So checking time. Okay, we're good. And so continuing the discussion on exposure, well, let me stop here for a second. See if there's any questions. No? Okay, so continuing with the concept of exposure, and this is important. What is the difference between direct exposure and indirect exposure? When we talk about this, and I have several examples here for you, we'll begin with direct exposure and contact, and I have a diagram here just to give you one example. And this is more applicable to infectious agents that are considered transmissible or communicable, and more specifically person-to-person transmission. So if you have a host that's harboring, that's serving as a reservoir of the infectious agent, they may or may not be ill, but they have the pathogen present. And there's some form of contact, again, depending on the agent. For example, if it's the influenza virus and there's close enough proximity, a cough or a sneeze, the droplets can contain the virus, the air becomes contaminated, and then potentially inhaled, and now the receiver becomes exposed. And if that agent now proliferates and colonizes, they've become infected. And if that infection is not controlled via the immune system, that can progress further into initiating a full-blown illness, such as the flu, right? And so this is person-to-person transmission, a very simple way of representing that. And you can see some examples of possible modes of this form of transmission. Taking this a little broader and going beyond infectious agents, infectious biological or microbiologic agents specifically, but also carrying this even broader, that can include chemical agents as well as physical agents. That brings us back to the four major matrices that we talked about at the beginning. And so once there's some source in the environment, whether it's indoors or outdoors, that results in contamination of a matrix by virtue of using the air, everybody has to breathe, so that means we're inhaling air. Using water, everybody uses water to drink, to cook, to bathe, etc. Using soil, whether it's direct or indirect, soil is involved and certainly linked with food quality, both vegetative and livestock based. These can become contaminated, and if the contamination is extremely high, we would say it's polluted. And if we have that interface, there's contact, we inhale the contaminated air, we ingest the contaminated water. And even though the focus here is on humans, it's the same mode if it's an animal, same mode if it's a plant. And the reason this is important is because the food chain can become involved as well. But this is what direct exposure is. There's that direct interface with the contaminated air that the human's inhaling, or the contaminated water that the human's ingesting. And the same could be said about the animals or plants. They don't inhale, they have transpiration. They rely on air. They can be affected by a poor air quality, such as elevated oxides of sulfur, ozone can adverse affect plants, but that's beyond the scope of what I want to present in this module. But simply that a direct interface between the contaminated matrix. All right. And so here's an example of a biological agent. This is specifically a zoonotic agent. And when I use the word zoonotic agent, just as a refresher for you, that means it's an infectious agent that is known to infect both animals. It's derived from animals and humans. And what we know is that greater than 60% of infectious diseases encountered by or experienced by humans are of animal origin. So they're zoonotic infectious agents, and it's somewhere around 63% of those illnesses associated with infectious zoonotic agents. So there can be direct transmission from air by inhalation using Mycobacterium bovis, for example, and this could be from cow to human, for example. There could be indirect transmission drinking the milk from that cow and ingestion. So inhalation mode, respiratory system, ingestion mode, gastrointestinal system, direct transmission, indirect transmission. Looking at a few more examples, and I won't go through them all, but just to continue the discussion. Direct exposure and contact to humans by inhalation, certainly the respiratory system, and can result in systemic. And these are the categories we look at: particulate matter, vapors, and gases. And I'll go into the distinctions of these a little later. But this is an example. And lead is a major culprit. Inhaled airborne lead dust or fume from contaminated air. And there are industrial sources such as battery manufacturing is an example. And these are some major issues, especially among younger exposed individuals. Direct exposure involving ingestion, again, the ingestion mode, gastrointestinal route, and so lead-based paint, if there's consumption intentionally or not, so young children known to, what's known as pica, consuming inanimate objects like paint and so forth can be exposed to lead. But nonetheless, whether an adult or a child ingesting lead can be absorbed from the gastrointestinal system and become a systemic toxicant and now adversely affect the nervous system, the renal system, just to name two vulnerable systems. And then a final one, just ingested herbicides such as atrazine, vegetables treated with the herbicide to control weed growth, but again, residual presence of the herbicide consuming the vegetables now is a mode of exposure, ingestion mode. And the same could be, or similar can be stated for the integument, specifically the dermal system. So I'll leave it at that. You'll have access to these slides with some examples. Here's one I just want to point out from agriculture exposure. This is a common trivia question, but organophosphate insecticides are highly dermal absorbable. So not only are they an inhalation hazard, but also direct contact because they absorb so readily across skin surface, and they're highly neurotoxic because they inhibit acetylcholinesterase. So agricultural workers have higher hazard potential, more so than the consumer. And this is an example I alluded to earlier. Okay. So let's shift our attention to indirect exposure and contact via food chain, food web, biochemistry, and so forth, and also involving vehicles or vectors. So you can see that with indirect exposure involving the food chain, this could be the contaminated matrix on the left, air, water, soil, for example, and the contaminant, whether biological, radiological, or chemical, can contaminate a plant source. And an animal may be grazing on those plants, and now by virtue of consuming the plant, depending on the agent, it can accumulate in the animal. It may or may not result in an adverse impact or illness in the animal. It depends on the level. It depends on the susceptibility of the animal as a result of that exposure. But whether the animal is adversely affected or not by virtue of being contaminated, if human now consumes that animal, the human becomes exposed. And therefore, their hazard potential is now increased. And again, as stated, as you increase the hazard potential or the level of exposure, along with numerous other factors, it increases the risk of initiating an adverse response, otherwise disease or dysfunction. But there's also transmission indirectly involving vehicles, which are inanimate objects, otherwise known as fomites. So this is these examples more in a foodborne establishment where cooking utensils are not sanitized appropriately, and they're clean. They can serve as a means of a vehicle to transmit an infectious agent to a human, or contaminated food or contaminated water. From this perspective, these can be vehicles of contamination. Vectors involve living organisms, so tick-borne diseases, mosquito-borne diseases are examples. And so this diagram takes indirect exposure with specificity focused on contaminated reservoir or host. A vector becomes contaminated based on feeding off the host, for example, and then interacts in some way, biting, and transmits the infectious agent to the human. Now they're exposed. So this would be a diagram that represents that simple transmission involving a vector. And examples of some are mosquitoes and ticks and rodents, flies, and then here's a good diagram on the right. And here's some major tick-borne and mosquito-borne diseases in the U.S. Malaria and yellow fever, not so much, but these listed here are really pretty much worldwide, but include the U.S. Tick-borne, mosquito-borne. But also going back beyond infectious agent and now looking at examples involving chemicals. Here's another one involving lead. So let's say there's a mother who has a young child who's nursing, so a neonate, inhales airborne lead, and the lead from the contaminated air becomes systemic in her circulation. It may or may not be at a level that results in manifestation of illness to the exposed mother, but the level may be high enough that once it's systemically, it can be present in the mammary milk, and lactating child consumes that milk, and now they're indirectly exposed to the lead that originated from this source. So this is an example where in some respects the mother is almost serving like a vector, so to speak, but it's indirect exposure because it was the mother that was directly exposed, not the child. And then there can be, depending on the rate of exposure, the duration of exposure, the level, it can result in adverse impacts to the child. We see this in the food chain as well. Contaminated water, well, if we drink that contaminated water, that would be direct exposure. But if we consume fish that became contaminated by virtue of living in the water, and I show a congener of a polychlorinated biphenyl structure here, which is highly fat absorbable, it can now, the fish from this water, it can absorb in their tissues by virtue of being lipophilic or fat soluble, and human consuming this fish, it can become easily absorbable and therefore systemic and result in adverse impacts to the individual exposed. And we can see this with livestock as well. So then, does everybody who's exposed get sick? And the answer is no. There are a variety of factors associated with the vulnerability or susceptibility or risk of disease resulting from exposures, whether it's infectious biological agents or toxic chemical and toxic physical agents. And so this slide shows a list, and all of these are important. Some are more relevant to chemicals as opposed to biological agents, but most of them cross the spectrum. So what I mean by that is whether it's biological, chemical, or physical agent, in almost all cases, most of these factors will determine the level of vulnerability or susceptibility to initiating an actual adverse response. So the point is, just because there's external exposure doesn't mean disease is going to occur. It may increase the risk, but it doesn't necessarily mean that disease is inevitable. And even if internal exposure occurs, that same statement holds true. There are a variety of confounding factors, beginning with these first two, but certainly not including only these first two factors, categories of factors. So there's this concept of dose response, and this is a log normal distribution, and in general with chemical, biological, and physical agents, there is this relationship, doesn't always come out such as clean as this, because you can have plateaus and so forth shown by some of these other examples, but certainly as you increase the concentration of exposure, you increase the percentage of those organisms that are likely to manifest some measurable, I should say, detectable or diagnosable adverse effect. So let's break this down with some specificity. These are key factors, 4 key ones relative to infectious microbiological agents. It's the infectious model, the immune response. So host immunity, which again is influenced by a variety of factors, including health and age. So even there's multiple confounding factors involved, the virulence of the agent involved, and how much are you exposed to, and what is the duration of exposure. Now, one distinction among others, but one distinction between infectious biological agents relative to all chemical agents and all radiological agents is this concept of proliferation. So organisms, viruses can infect cells and then the cells proliferate. Bacteria can proliferate, fungi can proliferate, whether it's the gastrointestinal system, the respiratory system, the dermal system for that matter. Chemicals don't proliferate. Radiation does not proliferate. So that is another component. So the concentration of external exposure can actually change if there's a proliferation and colonization of the organisms involved. And so you'll see some similarities here, which I did intentionally when we look at toxic chemicals and radiological agents, health of the exposed individual. And this can include immune system, but also biotransformation, phase 1 and phase 2 metabolism activity can be involved. And then the inherent harmful characteristics or potency of the toxic chemical, or the potency related to the energy of the physical agents. And of course, amount of exposure and duration of exposure. Okay, and then it's a complexity here is it's not always the parent compound resulting in the initiation of the disease. That parent compound can undergo changes to either detoxify it or increase the toxicity before it actually initiates an adverse effect by accumulating at a target site. So that's the purpose of that diagram. And then moving to exposure factors of toxic sound. We typically don't talk about sound being toxic. In fact, most publications, even including some of my older publications, don't even talk about sound as being an air contaminant. But sound is a physical agent, just like non-ionizing radiation and ionizing radiation, and it's present in the air, and therefore it's an air contaminant. And at certain levels, it can be toxic. It can result in physiological changes, right? And by definition, that's what we use as toxicity. And there are a variety of factors involved. But with sound, we have a few other characteristics. When we look at sound, we first asked, what is the frequency? And A scale is a great trivia question. Refers to 500 to 10,000 hertz. It represents the A scale. This is the range of frequencies. Remember, frequency is the wavelengths, the number of wavelengths within a given period. So on the right here, looking at this diagram, you can see high frequency relative to the first block on the far left, low frequency. High frequency, higher amplitude. Low frequency, low amplitude. So you can see the comparisons of using an oscilloscope to measure sound waves, sound energy manifested in sound waves. My point is this: with sound, in addition to how much or the health of the individual um, and the duration of exposure, we need to know the frequency. We are most vulnerable within the range of 500 to 10,000 hertz. And the significance of that is a human being with perfect hearing can detect sounds within the range of 20 to 20,000 hertz. So that would be a newborn baby, for example, with perfect hearing. Over time, with aging, our hearing acuity decreases, but in terms of vulnerability for noise-induced hearing loss, we talk in terms of measuring sound for human exposure assessment using the A scale frequencies. And then we ask the question, what is the amplitude, the loudness of that sound? And that's the amount. We measure that in the logarithmic scale of decibels. So we express measurements of sound relative to human exposure assessment, impact to human using dBA. So when you see dBA, it refers to the decibels represent the loudness. For example, 85 decibels is the loudness, the amplitude of the sound pressure level, and A means the sound pressure level, the loudness within the A scale frequencies. Okay, so I include this for you. And we shift some major contaminants then, major categories of air contaminants indoors and outdoors. Looking at the air matrix, you should know what PM stands for. PM stands for particulate matter, and particulate matter that is of most concern, not the only concern, but the most concern is PM less than 10. So you'll see PM10 or PM2.5. The smaller the equivalent diameter, that's the size of the particulate matter that's airborne, the more inhalable and respirable, meaning the deeper into the bronchial tree. And when it reaches about sub-micron, 1 micron or less, it actually can cross from the alveoli and become systemic in the circulation. But all levels, total PM, upper respiratory system in terms of upper respiratory system irritation, and even some vulnerability to nasal cancers from certain chemicals. It would involve the larger particle sizes, meaning greater than 10 microns. But the most hazardous particulate matter are those that are less than 10 microns, and PM2.5 is the primary indicator for that. And then we have gaseous chemicals, including vapors from volatile liquids and solids, those substances that evaporate. So inhalation mode, respiratory route, primary concern. And here's a list of some common concerns by contaminated air. And it's not all respiratory. You can have contaminated air and the direct contact can result in impacts to the dermal system. But once inhaled contaminants become systemic, a myriad of organ systems, central nervous system, peripheral nervous system, can be involved. And so you should be familiar with just some key points of the Clean Air Act. The Clean Air Act addresses emissions from both mobile, so vehicles, so automobile emissions, and stationary, so factory type emissions. And there are 6 criteria pollutants. There's a link on the slides, but I list them here. And before we come back to that, you should know the distinction between a primary air pollutant and a secondary air pollutant. Primary air pollutant is the form it existed in at the point of discharge. So oxides of nitrogen, such as nitrogen oxide, would be discharged from the smokestack or the automobile exhaust. Once it's in the atmosphere, it interacts with sunlight, for example, and perhaps even other chemicals in the air, can form new pollutants in the air. It may undergo photolysis and form nitric oxide, NO, instead of NO2. It can interact with water in the air and form nitric acid, which is a major component of smog forming peroxyacetyl nitrate if it combines with other organic molecules. So smog, you think of PAN, and that's formed as a secondary air pollutant. And looking at the 6 criteria pollutants, as per the Clean Air Act, these are some major adverse effects associated with them, all of them involving really the inhalation mode. And here's the other 3, but I want to point out 2 of them here. Again, going back to nitrogen dioxide, not only does it contribute to the formation of smog, but it can react with water and form nitric acid, which makes rain and other precipitation, snow, unacceptably acidic. So we call it acid rain or acid precipitation. And going back to the prior slide, sulfur dioxide is the other major component. It's associated with inflammation, can exacerbate other things, but it also, similar to oxides of nitrogen, can interact with water in the air to form, in this case, sulfuric acid, which is the second major component. So both sulfuric acid and nitric acid are the 2 major components of acid precipitation. And then shifting down here, as I've already alluded to, particulate matter, the ones of major concern are those less than 10 microns, so we'd say PM10 or PM25, even more so because it's even smaller and can go deeper into the respiratory system. The subscript 2.5 means the equivalent diameter of that component of the particulate matter has an equivalent diameter of 2.5 micrometers. It's a little more involved than that, but in general. We talked briefly about airborne radiologic agents. Ionizing radiation is an air contaminant. Radon gas is the most common one of concern, or I should say at least in terms of awareness. There are multiple agents of concern, but it's certainly a major one from an environmental public health perspective. And this diagram is one I showed you earlier. So radon gas accumulating indoors contaminates the indoor air. Non-ionizing radiation, microwave ovens indoors, various electronics, computers indoors is improved, as I mentioned earlier, and then outdoors, natural sunlight, high tension wires, a lot of controversial toxicity data and epidemiological data regarding this, but nonetheless, both ionizing and non-ionizing concerns. But the examples shown on this slide are all examples of non-ionizing radiation. Electronics, including electric blankets, whatever, microwave ovens, high tension wires, sunlight. And thirdly, sound. From an environmental public health perspective, it really is more community-based noise and traffic and transportation. Trains, planes, automobiles, right? Nightclubs, proximity to manufacturing industries, among others, can contribute to community noise. And then the final stage here of this module is looking at water matrix and air and food as 2 additional major matrices. You know, here's the categories of both surface and groundwaters that can become contaminated, but we also talk in terms of wastewater that is produced as a byproduct of human activity and reintroduced back into the environment. So these are different sources of contaminated water. So it's not just what we drink and cook with, otherwise known as potable, but what we use for recreation, fish we consume, water that we use for showers and bath, humidifiers even, right? You can have protozoan growth, bacterial growth, water storage, think of Legionella infections. And so here's a list of some very common infectious agents And these are gastrointestinal illness being the primary, but certainly not the only one. Legionella here, you can put, it's really pneumonia, so the respiratory illness is really certainly involved with Legionella. But this is a list of some very common ones that we deal with, and these are some examples of common illness. So, Pseudomonas in hot tubs is linked with swimmer's itch and ear infection and dermal rashes, for example. Major federal regulations where you had the Clean Air Act for air, we have the Clean Water Act for water, and we talk in terms of point pollutants where there's direct discharge from a identifiable source, and then non-point, which is runoff. So think agriculture, think stormwater, and so forth. And so Clean Water Act regulates both point sources and runoff discharges. And there's some links here. And we look at the Clean Water Act really addressing wastewater treatment facilities. And here's a diagram of wastewater where we have concerns over what's coming in as an influent. And there's typically at least two phases: separation of solids, stabilization of pathogens, but more often than not a tertiary phase, perhaps a treatment to separate certain chemicals, and then tertiary phase of disinfecting to a certain level prior to discharge into a receiving body of water, a lake, a river, for example. And simultaneously, during the treatment of the influent to render an effluent, which is discharged into a receiving body of water, there's also generation of biosolids that we otherwise call sludge. And sludges are nutrient rich, but raw sludge is also rich in infectious agents and or pathogenic agents, and it needs some form of treatment or stabilization if it's going to be used for agricultural purposes, such as fertilizer. Otherwise, it can be treated, it can be landfilled, incinerated. There's other uses as well. And so we have large-scale municipal wastewater treatment. That refers to the used water. You should know that it's usually UV light or chlorine or ozone. One of those is often used prior to discharge of the effluent. But that effluent, even with some level of disinfection, is not potable. And before I get to potable, just mentioning small-scale on-site treatment. So septic systems and pit privies or an outhouse or a septic system with distribution are small-scale on-site systems designed to do something very similar to stabilize the waste, but it's certainly not the same. So large-scale municipal wastewater treatment, small-scale on-site home treatment. And these are major indicators of water quality. Biological oxygen demand is a key one. The higher the biological oxygen demand, there's a direct relationship between labile organic matter. So the goal of treatment is to decrease the BOD. And so how do we know when the influent has been treated enough? You measure the biological oxygen demand. It should have declined substantially. Fecal coliform, which is an indicator organism of fecal matter from warm-blooded animals, should be low, among others, but there should also be, in the case of chlorine, if that's the disinfectant, there should be an acceptable dose with residual. But when we talk about water treatment, it's regulated by the Safe Drinking Water Act, also under the EPA, but Clean Water Act is for wastewater, Safe Drinking Water Act for potable or drinking water. So we talk in terms of, you should know the distinction that water treatment means potable water treatment. Wastewater treatment refers to treating contaminated water for discharge back in the environment. Water treatment is for distribution for drinking and cooking purposes. Right? And we have large-scale municipal water treatment facilities, and we also have small-scale on-site where groundwater systems, where water is pumped from an underground aquifer. So surface water, groundwater, large-scale, small-scale. Simply to know the distinction between the two. Both of them require measurements to make sure that the levels of biological agents, but also chemical agents, and even some radiologic agents fall below the MCL, the limits as per the Safe Drinking Water Act. And finally, the food matrix, just to point out, bacteria, viruses, various parasites in the form of protozoans and helminths can, and there's a lot of crossover between foodborne hazards and even waterborne hazards. It's not only biological in nature, so I put this slide in to show there also be chemical contaminants. There can also be debris during food prep and food manufacturing or processing, and even radiologic agents. But we tend to think of foodborne hazards and related foodborne illnesses solely from the microbiological level, and that's fine, but it's really a little broader than that in actual practice. And so food handling requires certain precautions, and storage and serving and cooking requires certain temperatures, and so there's some links here for that for your use. But you know, typically to cook meats, poultry, beef, pork, minimum of 140 degrees Fahrenheit to 160, 170 degrees for internal temperatures to ensure that any pathogens present are denatured and destroyed, but also handling is certainly part of this as well. So those are some links. But answering the question, what are some common agents involved as far as viruses? The norovirus would come to the top. So most foodborne illnesses are linked in the US to the norovirus, then followed by many of these, if not all of these, not necessarily in order, but norovirus being the most common one, but any one or more of these can be involved. Gastrointestinal being the primary illness reported, both food and waterborne, but there can also be more systemic neurologic effects as well, but certainly the gastrointestinal system in general. Contaminated matrices, food quality is directly related to air quality, water quality, soil quality. I should have put irrigation water in here too for vegetation. And here's the stages of foodborne illness. And there's certainly, and this holds true for waterborne consumption too, so including beverages, there's often a lag time in either upper or lower gastrointestinal distress or both. So there's a process. You certainly don't need to memorize these 7, but you should be familiar with the hazard analysis and critical control points approach, HACCP, which is a way to prevent. So in the manufacturing side of food growth, all the way to food processing, to food packaging and distribution, to assure that primarily pathogens, but it goes beyond pathogens. So from a preventive standpoint, to decrease the likelihood of any foodborne related illness. So HACCP is a preventive approach to handling foodborne. And these are the focus areas. As I said, it goes beyond infectious biological agents and includes some other factors. Physical from this perspective would be like debris in food, and it's the full from material production all the way through distribution and consumption. And I want to close this session. The only reason I included this, I noticed, and I went through, again, multiple sources of review materials for the CPH along the issue of environmental public health, and I came across one question asking about One Health. And so the conventional, if not the original paradigm, and this is from CDC, is it looks at the interface of people, animals, and the environment, not just people in the environment, which has been the focus of what I've been presenting today, but recognizing that really more than 6 out of 10, more than 60% of infectious diseases in humans are spread from animals to humans. So this is a more integrated approach, so that rather than simply looking at contaminated environment and potential exposure sources to people or the environment and animals, looking at them collectively in an integrated, so looking at that interface between them all. Having said that, at Ohio State, we've expanded this paradigm. We include plants, and we've expanded the paradigm to include chemical. My point is not to tell you what we're doing here, but the original paradigm was the foundation, catalyzed by infectious agents, specifically zoonotic infectious agents, but this model can apply beyond biologic agents and can include toxic chemicals, can include toxic radiologic agents, sound, and so forth. So the environmental contaminants can be broader than the biological. It can include chemical and physical. And the organisms, humans and animals, can also include plants as a third category. So, but from the perspective of understanding One Health, human, animals, and the environment, that interface is the original paradigm. And so this is just a diagram of those three components: human health, animal health, environmental quality. Sometimes they say environmental health. It's really environmental quality. Okay? So looking at it in a holistic way is you can be a source of contamination or a receiver. And so this diagram, and it goes beyond humans and animals, it also includes plants, but just showing how contaminants can move through the environment, move through biological systems. I leave it at that. So I'm not going to go through the final set of slides. That was by design, but if you're interested in evaluation, there's a set of slides here of just the concept of collecting external samples to measure external exposure, what's in the air, water, soil, or food, how much is there, and then add what are the characteristics of the exposure, rate, frequency, so forth can be part of that. It can be occupational or non-occupational, and it can be ambient or indoor. Can involve one or more matrices simultaneously. It can even involve surfaces and building materials. And it crosses over into the biological matrices of the medical side of medical sampling as well, medical surveillance. And so this is what I mentioned earlier, is the interface with epidemiology, which was really not covered in this module, but knowing the external exposures to identify potential and real causes associated with disease if substantive exposure occurs, contrasted with the healthcare area, and it goes beyond medicine, but the adverse effects associated, and then using epidemiology to determine if indeed there are those causal relationships or there's some level of association involved. So I'll close here. If there's some time for a couple questions. We have about 10 minutes left. If anybody has any questions, I can try to answer it now. And if there's any requests for some supplemental information, just out of general interest, we can get that to you for any reasonable requests. So if you have a question, if you would type it in the chat. So I'll give you a few minutes or a few moments, and if none, then we will conclude this module.
Thank you so much, Dr. BFB. There are a few questions that I think pertain to everyone, and that's just on where to find these. And they are going to be located on the NBPHE website. And if you go to study resources, there are all different kinds of resources. And there is a line item that says CPH webinars. And then you can click on that, and you're going to have access to all previously recorded webinars.
Yeah. And I'll add that you're welcome. These are for your use, so you can use them to prepare for your exam, but anything beyond the exam, you're welcome to use these slides.
And we will be posting the slideshow as well, so you can go through and study and take notes. And in addition, there was a question about whether or not the webinars that we recorded prior to the new content areas, and it's structured a little bit different, but the content is the same. So whereas before environmental health was its own content area, now it's more incorporated into, across the 10 domain areas. So the content is still the same, it's just the way that it's organized. So yes, the content is all still relevant. And then also there is one more question. Let's see, Dr. Bissesi, towards you. It is, how is lead absorbed in humans?
Yeah, so it depends on the mode of exposure. So let's say contaminated air that's inhaled. If the particle size is small enough and lead in the elemental form can disassociate from particles, it can be absorbed across from alveoli into the systemic circulation. And depending on the amount and where it's distributed, it can have a target site such as the central nervous system. So the cognitive effects, it can target the peripheral nervous system. So it can result in ataxia or compromised movement of muscles, result to damage to the peripheral system. It can adversely affect synthesis of the heme group in red blood cells, resulting in anemia. And so those are just some three major ones. Trivia question is, if a child, so let me take that a step further. Everything I said, let's assume ingestion of contaminated water with lead. It's very similar. Less focus on interaction and adverse impact to the gastrointestinal system, although it can cause cramping and some gastrointestinal distress, but it can absorb into the systemic circulation and cause the same problems I mentioned: central nervous system, peripheral nervous system, anemia, as I mentioned. But a trivia question is, focusing on the ingestion mode, gastrointestinal system, is that young children absorb a higher percentage of lead in general relative to adults. And so that's why, that's one reason why, and in a classic example of the very young being more vulnerable, not to mention that they're still developing cognitively and so forth. So that's the long answer to your question. But also, it can be dermally absorbed if it's organic-based lead as well.
Great, thank you. Another question we have posed is, are foodborne illnesses considered direct or indirect exposure?
So it depends. If the scenario is if the food itself was not cooked properly, handled properly, and it's consumed, that might be considered a direct exposure because they're consuming it. Where it gets a little trickier is, in my opinion, is that if the food was contaminated with chemical residue and that was a result of where it was grown, and that residue remains in the food, then that would be indirect exposure because the food had that initial interface with the contaminated environment, and so the food initially became contaminated, and then the person who consumed it. But indirect exposure could also be discussed relative to pathogens as well. So it really depends how that food became contaminated.
Wonderful. Thank you so much. I don't see any more questions posed. And as a reminder, if you go to nvphe.org and click on the Study Resources tab, you'll be able to access not only these webinars, but other variety of study materials, as well as information on any in-person sessions that we will be doing. And again, if you have any questions, please feel free to reach out to info@nvphe.org, and we are happy to answer any questions you may have. So thank you for joining us today. Dr. Basesi, thank you so much for sharing. I think I've been through a lot of these, and I think I learned a lot. So I really do appreciate your time and effort, and I will end the webinar. Thank you so much.
You're very welcome. Thank you, everybody. Bye.